electron was discovered by J.J. Thomson in 1897 with the cathode ray tube experiment. J.J. Thomson constructed a glass tube which was partially evacuated much of the air by pumping it out of the tube. Then he applied a high electrical voltage between two electrodes at either end of the tube. He detected that a stream of particle ray was coming out from the negatively charged electrode, called cathode, to positively charged electrode, called anode. This ray is called cathode ray, and the whole construction is called cathode ray tube. There are three properties in regards to the cathode ray tube experiment. First, they travel in straight lines. Second, they are independent of the material composition of the cathode. Third, applying electric field in the path of cathode ray deflects the ray towards positively charged plate. Hence, cathode ray consists of negatively charged particles. A black body is a theoretical or model body which absorbs all radiation falling on it, reflecting or transmitting none. The special distribution of the thermal energy radiated by a black body depends only on its temperature. Black body radiation is the amount of radiant or heat energy emitted at various frequencies for specific temperatures of a black body. There are three characteristics for black body radiation. First, Planck's law of black body radiation, a formula to determine the spectral energy density of the emission at each wavelength at a particular absolute temperature. Second, Wien's displacement law, which states that the frequency of the peak of the emission increases linearly with absolute temperature. Conversely, as the temperature of the body increases, the wavelength at the emission peak decreases. Third, Stefan Boltzmann law, which relates the energy emitted to the absolute temperature. The quantum hypothesis was first suggested by Max Planck in 1900 when he attempted to explain black body radiation. He proposed that heat energy is emitted only in definite amounts called quanta. Thus, his equation became E equals to h multiplied by f. Planck maintained that only certain specific energies could appear, and they were limited to n whole number multiplies of hf. Thus, E equals to n multiplied by hf. With this equation, Planck was able to explain black body radiation, showing that the hotter the object gets, the more radiation it produces. Einstein won the Nobel Prize for Physics for explaining the photoelectric effect. He proposed that light is made up of packets of energy called photons. Under the photon energy of light, a photon is a discrete bundle or quantum of electromagnetic or light energy. If you shine light of high enough energy onto a metal, electrons will be emitted from the metal. Light below a certain threshold frequency will not cause any electrons to be emitted. It takes a certain energy to eject an electron from a metal surface. This energy is known as the work function, which depends on the metal. Electrons can gain energy by interacting with photons. If a photon has an energy at least as big as the work function, the photon energy can be transferred to the electron, and the electron will have enough energy to escape from the metal. The energy of a photon can be determined using the photoelectric effect, using the equation E equals to h multiplied by f. The mass of a photon has the value 0, which is assumed as the standard model of elementary particle physics. The momentum of a photon can be demonstrated by using the equation P equals to h divided by the frequency and wavelength of light.
The Compton effect is the term used for an unusual result observed when X-rays are scattered on some materials. By classical theory, when an electromagnetic wave is scattered off atoms, the wavelength of the scattered radiation is expected to be the same as the wavelength of the incident radiation. Contrary to this prediction, observations shows that when the X-rays are scattered off some materials, the scattered X-rays have different wavelengths from the wavelength of the incident X-rays. This phenomenon was studied experimentally by Arthur H. Compton, in which he used Einstein's idea of light as a particle. The Compton effect has a very important place in the history of physics because it shows that electromagnetic radiation cannot be explained as a purely wave phenomenon. Complementarity principle believe that a complete knowledge of phenomena on atomic dimensions requires a description of both wave and particle properties. The principle was announced in 1928 by Niels Bohr. Depending on the experimental arrangement, the behavior of such phenomena as light and electrons is sometimes wave-like and sometimes particle-like. It is impossible to observe both the wave and particle aspects simultaneously. Together, however, they present a fuller description than either of the two taken alone. According to the de Broglie concept of matter waves, the matter has dual nature. It means when the matter is moving, it shows the wave properties are associated with it, and when it is in the state of rest, then it shows particle properties. Thus, the matter has dual nature. Niels Bohr proposed the Bohr model of the atom in 1915 and is a modification of the earlier Rutherford model. The modern model of the atom is based on quantum mechanics. Although it contains some errors, but it is important because it describes most of the accepted features of the atomic theory without all of the high-level math of the modern version. The main points of the Bohr model are: electrons orbit the nucleus in orbits that have a set size and energy. The energy of the orbit is related to its size, and the lowest energy is found in the smallest orbit. Lastly, radiation is absorbed or emitted when an electron moves from one orbit to another. The Broglie hypothesis says that all matter has both particle and wave nature. The wave nature of a particle is quantified by the Broglie wavelength defined as lambda equals to h over p, where h is Planck's constant and p is the momentum of the particle. The reason that he chose the momentum equation over the energy equation is that it was unclear with matter whether E should be the total energy, kinetic energy, or total relativistic energy. This was called a hypothesis because there was no evidence for it when it was proposed, only analogies with existing theories. In 1927, physicists Clinton Davison and Lester Germer performed an experiment where they fired electrons at a crystalline nickel target. The resulting pattern matched the predictions of the Broglie wavelength. In conclusion, all the 9 subject matter in quantum physics is connected on a sequence, based from the first research, which is later developed into the next research, and so on until the 9th subject matter. The sequence of quantum physics starts with the theory of electron and developed into photon theory of light, which results in a theory of photon. This was then continued to create Compton effect, and also Planck's law was used in finding black body radiation. Those two then developed into the principle of complementarity and wave nature of matter. All of that leads to the Bohr model, And lastly, all the information and theory is then used to create the Broglie hypothesis. Thus, with all the sequence leading up to one another, the quantum physics timeline is interconnected.